In this video, we're going to be taking a look at an oscillating string that creates a standing wave pattern as shown to the left over here. And we have a 6 meter, 200 gram string that's oscillating 50 times per second. And we're going to find the force of tension in the string. So what we're going to do is definitely use a formula: velocity equals the square root of tension divided by the mass divided by the length. So if we find our V, our mass, and our length, then we're good to go, and then we can algebraically solve for the force of tension. So let's go ahead and see what we have and label some stuff first. So we have a 6 meter, 200 gram string. So we appear to have a length of 6 meters, and we have a mass of 0.2 kilograms. So we're going to divide that 200 by 1,000 to make sure it's in our standard unit of kilograms, and then it's oscillating 50 times per second, which means the frequency is 50 hertz. And then that looks like all we're given. So if we take a look at what variables we do know the mass and we do know the length. All we need is the velocity, and then we're good to go to algebraically solve for the force of tension. Now, in order to solve for the velocity, we aren't directly given it, so we're going to have to definitely use our wave formula, which is velocity equals frequency times wavelength. Now, we know the frequency is 50 hertz, so if we get the wavelength, then we're definitely good to go to complete this step and then slide the velocity up into our initial formula. Now, if I'm taking a look at my wave pattern, it looks like I have half a wave here, and half here, so I have 1.5 wavelengths total in my wave pattern. So I could look at this a couple different ways. We could use the formula wavelength equals 2 times the length over the n value, which is the harmonic number, and then that gives us the wavelength. Or we could take a look at it more conceptually and solve it that way. So let's go ahead and use the formula first. And if we use the formula, we would have 2 times the length of the string of 6 meters. And then for this string right here, if it was at its fundamental frequency or first harmonic, it would just be one node to the next node. So then that would be our first. So this is our second, and then this would be our third harmonic. So 6 divided by 3 is 2, and then 2 times the 2 up here would give us a wavelength of 4 meters. The other way you could solve for it, which is maybe less common and a little bit more conceptual, is you could say that you have 3 halves of a wavelength in a 6 meter tube. And then if you divide both sides by 3/2, then you also get a wavelength of 4 meters. So I like that method of using that conceptual version of this formula, but this formula is probably a little bit more standard. So either way, you'll get a wavelength of 4 meters. So 50 times 4 gives us a nice even velocity of 200 meters per second. And then we can go ahead and do our final step. So we have 200 meters per second equals the square root of the tension divided by the mass over the length. So let's go ahead and do a quick little side calculation of the linear density, 0.2 kilograms divided by 6 meters of length. And that gives us 0.033 kilograms per meter. So that's our mass over our length, which is our linear density. So we can go ahead and put that 0.033 in there. And then basically what we're going to do is we're just going to end up squaring both sides to get rid of the square root, and then multiply both sides by 0.033. and then our tension comes out to 1,320 newtons. So if you're looking for the tension of a string, very likely you are going to be starting with this as your foundation. Velocity equals the square root of T over M over L. And then write down all of your known variables, plug in the things that you are able to plug in, and see what you're looking for. Oftentimes you'll need to find a wavelength and do a little side calculation as we did over here in green. I didn't necessarily have to do the linear density in orange over here, but I decided to just to simplify that into a single number for our denominator. And then from there, just squaring both sides, multiplying both sides by that denominator, and I got a final tension of 1,320 newtons. So I hope that was helpful to you. Thank you very much for watching and listening.